Today's webinar speaker is William Oberkampf. Dr. Oberkampf has extensive experience in research and development in fluid dynamics, heat transfer, flight dynamics, and solid mechanics, serving on the faculty at the University of Texas at Austin and then continuing on to Sandia National Laboratories. During his career, he has been deeply involved in both computational simulation and experimental activities, and in the last 20 years, he has been focused on verification, validation, uncertainty quantification, and risk analysis in modeling and simulation. He retired from Sandia as a distinguished member of the technical staff and is a fellow of the American Institute of Aeronautics and Astronautics. So without further ado, I will hand the connection over to Bill to introduce us to the topic of verification, validation, and predictive capabilities.
Oh, thank you. Thank you very much, Lorraine, and the CIG for inviting me to give this presentation in this webinar. This is a topic that is getting a lot more attention over about particularly the last 5 to 10 years as simulation takes much more importance in design and certification and also in assessment by regulatory authorities. So today I'll talk about verification, validation, also calibration, and predictive capability, and try to distinguish what the different ideas are. I want to give a little bit of motivation and background of this is simulation in general, not only for geodynamics, but most of the terminology and the concepts have actually come from the engineering side, mainly from fluid mechanics, heat transfer, solid mechanics, and structural mechanics. I'll talk about the various verification activities. They're divided now into code verification and solution verification, and try to make the point why they are important. That is the foundation that we build on. Model validation and calibration are two very closely related ideas. And in the field of geodynamics, geosciences, calibration is very important. In fact, you could argue that it's maybe even more important than a model validation. In engineering, the perspective is very heavy on also model validation. And then I'll talk about predictive capability and non-deterministic simulations, and then I'll close with a few remarks, and I'll be glad to answer questions at the end of the webinar. I think it's hard to realize that we are in the midst of a revolution in science and engineering. When you're in the midst of rapid change like this, it doesn't seem all that spectacular, but if you take a historical perspective, it is absolutely stunning. I'm an old enough guy that where I can say, and maybe there's some older people also online, I grew up as an engineer learning on a slide rule. Those days are gone, and so I can much more easily, especially compared to the young people, relate to how things have changed. The impact of modeling and simulation are dramatically increasing in geophysical systems because there are some very special capabilities that you have and difficulties that are that you cannot overcome. Traditional experiments for the understanding of your systems are usually impossible because you have large physical systems in terms of both either atmospheric or underground facilities or various man-made facilities and how they interact with the environment. You have large physical scales and long time spans, and it makes simulation very appealing. And it allows you to do something where you can look potentially years or even centuries in the future, and of course then the issue of what is the credibility of that simulation when we can magically advance time with our simulations. We can also optimize and perturb our designs in unique ways, not only the effects of, let's say, nature or man-made events, earthquakes, tidal waves, and so on. And that is a great capability. Sometimes it's referred to as scenario analysis. And we must not forget that the reason we are all at this point in history is because of the stunning reduction in the cost of computing. If we would not have that reduction in the cost of computing, we would not be here today with this topic. So the fundamental issue that I want to address is how can simulation analysts and customers who use simulation determine if the simulation results can be trusted. And sometimes I'll refer to the simulation analysts as suppliers of information, and the customers are your customers if you provide these simulations. These could be regulatory authorities, government authorities, or it could be a for-profit organization. What elements determine if suppliers, and the supplier here is in the sense of a supplier of a computational simulation. In some of the writings that I've done, and particularly in the book that Chris Roy and I have completed a few years back, we try to make that point of computational analysts are really suppliers of information. That's what you provide to a customer or, let's say, a regulatory authority. What the key elements are, of course, always have been in any technical field. It's education and training of the computational analyst. And I'll usually use the broad term computational analyst, but I also mean the modelers that build the mathematical models. Development and implementation of quality control processes for simulation activities. If you do not have a process that is repeatable and that you can document it to particularly a regulatory authority, then you do not have a real quality control process that you can prove what you have done. Sometimes in engineering, there's a relatively new term referred to as simulation governance, but it also applies in any field of simulation. And then, of course, what we'll stress here today is the use of verification and validation activities and the estimation of uncertainties that could impact the results. Sometimes it's called UQ, uncertainty quantification, but I'll use the term commonly predictive capability, which is a more comprehensive term. In this area, people should realize that there are really three different ways that the terms verification and validation are used. There's system V&V, and that term is primarily used in the engineering system world, where they talk about V&V of systems. And that's a very useful concept. They have developed a large literature, a number of books, and of course publications. And that is for testing out your system. For example, hardware in the loop system on aircraft control systems or any sort of automatic control system. And then there's another field which is more, it's broadly based, is software V&V. And that has a long tradition, but it has a different emphasis. And what we were going to be specifically referring to is simulation V&V. So when you talk with other people, you have to understand what they mean by these terms V&V. And for this community, you'll run across computational scientists or computer scientists that will use the term. What they mean by V&V is really a software V&V. But we're talking about the emphasis on simulation. All of these have similar concepts, and verification generally has the idea of, am I building the product correctly? The product meaning software or the simulation result itself. And validation, and I'll more formally define these in a little bit with regard to both engineering and computational sciences. Am I building the correct product for validation? Meaning I'm building something that the customer is interested in answering a question to. So we will focus on simulation V&V, and particularly on the idea of predictive capability. The conceptual framework for simulation, verification, and validation of predictive capability. This gives you an idea of what the philosophy is and the first idea of how you separate these ideas. The first one is that verification and validation are built on the philosophy of skepticism. That may sound like a weird thing to say, but when you're in it a long time, like I've been, roughly 20 years, maybe a little bit longer, and how you distinguish that from predictive capability or uncertainty quantification, this is really testing. That's the emphasis in V&V. Testing of software, testing of our models, testing of our assumptions in the models, all of those kinds of things. Another way to say it is, show me the evidence that the software and the mathematical models are working properly, meaning what you think they are supposed to be doing in the mathematical model. Because the mathematical model, you have to remember, is a model which is separate from the discrete model, which is in software. And I won't have time to go into that a lot today, but that's a separate model. Okay? Predictive capability is foretelling the state of a system for conditions where no experimental data are available. That's a very special use of the word predictive capability. And it's getting more commonly used in the engineering community to segregate the idea from what is particularly the idea of validation. So we are telling, we claim that we can make a prediction of the future with our models. Predictive capability is primarily, it is fundamentally built on the fidelity of the physics of the modeling that is embodied in the mathematical model. That is, the physics in the model. Some people, particularly if you come from a statistical background, you think that predictive capability is primarily a statistical process. That's an important element, but predictive capability that is foretelling the future is based on physics and science and chemistry, biology, all of those things, where statistical techniques are tools that you get there. Identification and estimation of all sources of uncertainty for the system conditions of interest. And this is a vast topic in itself, particularly if you deal with systems that are exposed to very different kinds of environments. For example, tsunamis, earthquakes, all different kinds of systems that can be exposed to floods, all kinds of things. The procedure is built on uncertainty quantification using non-deterministic simulation. And at the end of the talk today, when I get into predictive capability, I'll particularly talk about that. Predictive capability is the primary reason for conducting simulation. And the reason I say that is that some people say, you know, it's really all about validating your models. Well, that's an important piece. But we are primarily building models, spending a great deal of money and time on making predictions where there is no data. So now into the more formal definitions. This is a definition that's been around now for a little bit over 20 years. It was first codified by the Department of Defense, American Institute of Aeronautics and Astronautics, American Society of Mechanical Engineers, and now recently adopted, at least to some degree, by American Society of Civil Engineers. The process of determining that a computational model accurately represents the underlying mathematical model and its solution. It is a very specific definition, and it only refers to mathematical computational issues. Another way to say it is verification assesses software reliability and numerical accuracy. One way to draw a simple picture on this is you have a mathematical model, which I mean usually it's a partial differential equation. It can be an ordinary differential equation, it could be an algebraic equation. But we usually are interested in partial differential equations for field problems, elliptic and boundary value problems, for example. Then you have the mapping of that mathematical model, which only exists as a calculus problem, typically. And it is mapped to a computational model. And here I use that term, but it's actually a discrete model. And a discrete model exists not only in the discrete world itself, and it also exists primarily, we're interested in software. And that fidelity of that mapping is one aspect of verification. And then the mapping of that, let's say specifically software, the embodiment in software, into a computational result. The accuracy of that calculation is also an aspect of verification. And those two particular pieces I'll talk about in just a minute. The first type of verification is code verification. Code verification are activities that are directed toward finding and removing mistakes in the source code, finding and removing errors in the numerical algorithms. Those are actually two different activities. Bugs in the source code, people are familiar with those, and that's one thing. And some people think that a bug and a numerical algorithm error must be the same. No, they're actually different kinds of sources of errors. Numerical algorithm errors can actually, they're not necessarily a bug at all, but they can be weaknesses in the algorithm itself. For example, convergence issues or inconsistency issues. The primary result from code verification is the, let's call it experimental determination. That is, by testing your software to determine the observed order of numerical convergence. Sometimes it's called numerical accuracy. It is the observed order of numerical convergence in space and time. You can have other independent variables besides space and time, but that is the primary result, and that is very rarely done. Responsibility for code verification activities. Primary is the software developers. These can either be commercial activities or developers at a university or a government organization, any of these. But they're developers of the software itself, primary responsibility. But we should not forget that there is also secondary responsibility of simulation analyst. That is, you provide information for customers of your product to your customers, but in one sense, you are a customer of the software developer, whether it's commercial or university software. And you are in the responsibility of customers of the simulation itself. For example, if you were a regulatory authority and they ask you what has been done in code verification, that is a very appropriate question. Frankly, what is the status of code verification? Commercial software, very few, if any, document the observed order of accuracy or the observed order of convergence of their solutions. It's just very rarely done. In engineering, a number of organizations are improving significantly in this, but it is still rarely done. For different types of organizations that prove software, for example, universities or the government, very few actually compute it because it's a computed quantity. It's an observed quantity. It is a test result from the code verification activities. And there are many activities that go into this, and in our book we have a number of ways that you go in. But on this talk, I just have one slide on code verification. But you have to realize that all of our simulations are built on the reliability of the code and the numerical algorithms. And the code is an embodiment of the mathematical model. So if you are not doing, let's say, observed order of accuracy testing on your software, please look into these topics, because that is the real proof, as opposed to you say, well, what other kinds of, we have observed order of accuracy of second order or fourth order. Those are all claims of the numerical method, but a code observed order is actually a demonstration of what it is. The second type of verification is solution verification. These are activities that are directed toward assuring the correctness of the input and output for each problem of interest. That is, you may have different scenarios. You may have different earthquake environments or tsunami environments. Each one of those is an individual simulation, and to be sure you're using the correct input, and I'll talk more about that later, all of the parameters, the geometry, the characteristics of structures or watersheds or whatever it is, and the output data. And then the second one is estimating the numerical solution error in your numerical solution. There are 5 different sources of numerical solution error. People don't usually think about most of them, but this is what they are. Round-off error, which we almost always ignore, but of course it is always there because we have finite precision machines. But if we're operating on either 16 or double precision 32-bit or 64-bit machines, we have usually that's not a problem. But it is still something, particularly for long-time solutions, that can pollute a solution. Iterative error is almost all problems have some sort of iterative solution technique. They can be, you always have iterative techniques on large elliptic problems, but even on parabolic or hyperbolic problems, you will have iterative techniques as you advance, let's say, a time step. And then discretization error is usually the most troublesome because this requires a fine enough mesh or element size. You use finite elements, for example. And then there's a completely separate source, which is statistical sampling. If you have a non-deterministic simulation, it actually produces multiple simulations. And for example, if you have a Monte Carlo simulation, you may have hundreds or thousands or tens of thousands. For example, if you want to calculate the probability of a rare event. And then almost all significant, particularly in Bayesian estimation, you will construct response surfaces. Sometimes they're called metamodels. The construction of those surfaces, in fact, you couldn't do Bayesian estimation without them. But the issue is you have to realize that the construction of those response surfaces involve error, and you should try to estimate what they are. So the primary goal is estimation of total numerical solution error in the system response quantities, and I'll refer to that as SRQs of interest, or at least find out what the sensitivity is. That is a qualitative estimate of accuracy. In solution verification, there are two general classes of discretization error estimators, and these are discretization error. Of course, these are in discretizing time and space primarily, but certain problems you would also discretize, for example, energy levels, or you would have, let's say, frequencies. Discretization error estimators of type 1 are based on higher order estimates of the exact solution of the PDEs. And for a number of you, I suspect you're familiar with Richardson extrapolation, and it is probably the most popular because it is so widely, it is very easy to use, and it's basically a post-processing technique. Then there's order refinement methods and ordinary differential equations where you have adjustment of time step. For example, you almost always use order refinement methods as opposed to Richardson extrapolation, and finite element recovery methods. The second type of discretization error estimator is based on estimating the discretization residual of the PDEs, because you are only solving the discrete model. You're not solving the continuum mathematics model, that is the calculus problem. So you have different approaches there. There are transport equation method, finite element residual methods, and adjoint methods, which are getting very popular. And the reason they are is because they are extremely efficient in terms of very quickly getting estimate. Responsibility for solution verification. Sometimes it's called calculation verification. The primary responsibility falls on the shoulders of the simulation analyst. You call it computational analyst if you like. But there's also responsibility of the software developers. And you might say, why would I say software developers? Because to do these, for example, Richardson extrapolation, which is the one I'm most familiar with, or order refinement or finite element recovery, these are pretty significant pieces of software in themselves. And most computational analysts say, I would use that error estimator if it was provided as an option, let's say, in the software. So there is a responsibility for software developers to develop these tools, to make them easy to use. And then the secondary responsibility is on the customers of the simulation. That is, you provide information as an analyst to a customer, whether it's in government or wherever it is. And it is very appropriate that they ask, what did you do to quantify the various sources of numerical solution error? What is the status, at least in my opinion? Very few analysts estimate solution error. Even in engineering systems, it's still relatively a rare situation, whether you see either a conference paper or whether you see it in journal papers. Very few managers or decision makers ask about solution verification or calculation verification. It is a state of affairs that we definitely need to move beyond. Sometimes people will say, well, why should I do let's say, group refinement or time step refinement? Because I agree with the experimental data. That's a bogus argument, completely bogus. And you might say, oh, but I agree with the data. You have to realize that in simulation, there are many, many different sources of uncertainty and error that combine, and when you agree with the data, you could just be lucky. Or typically the problem is you have a very highly calibrated model, or saying it in a different way, as you refine a mesh or a time step, you will actually move away from the data, and that shows you there are compensating errors, which is a very common situation. So the formal definition of validation, was also formulated by the Department of Defense about 20 years ago, and AIAA, ASME, and ASCE. The process of determining the degree to which a model is an accurate representation of the real world from the perspective of the intended uses of the model. This is a diagram that we put together as part of an ASME committee in solid mechanics, which I've been on ever since we formed the committee a number of years ago. And you say the intended use to simulation, whatever you'd like to call it. You have modeling activities, computational activities, and then you have experimental activities and measurements from nature. And those you take, each one has its own elements, and you compare those in the validation step. So validation deals with physics modeling fidelity, and particularly an assessment of physics modeling fidelity. And I'll contrast that with calibration in a little bit. And then you have the issue of whether it is adequate or inadequate for your particular application. And then you go on if it is adequate for the application. And I have similar diagrams to this later on to make the point of what are all the different aspects that go into this decision making. Let's talk about goals and tools of validation. Some of the tactical or near-term goals of validation are quantification of the effects of mathematical modeling assumptions and approximations by comparison of simulation results with experimental measurements. Typically, what you try to do is the quantification of what's called model form uncertainty. Model form uncertainty, for those that have not heard the term, it is a very specific type of uncertainty source. It is due to the approximations and assumptions in the model. Every mathematical model, no matter what you have, it always has approximations and simplifications. And trying to identify that is actually quite difficult. And you might say, why is that difficult? And the reason is because it is commonly mixed with what's called parametric uncertainty. That is uncertainty in parameters to the model. Input parameters is the general category. So that is separate from the quantification of model form uncertainty itself, as opposed to parametric uncertainty, and that's where calibration comes into the problem. The strategic goals, I would say, are the improvement of mathematical modeling to increase predictive capability. So in this formulation, in this conceptual view, validation is one of the key building blocks, just like verification, code verification, solution verification, to predictive capability. We want to improve the separation of model form uncertainty from input parameter uncertainty. In the geosciences field that most of you are in, that is a very difficult thing, and that's one of the things that makes your field, I feel, more difficult than most engineering fields. And I'll point that out a little bit later. What are the primary tools of validation? High-quality validation experiments. And in geosciences, you might say, well, we never have those on a field scale, complete scale, but you have experimental scales or laboratory scales, and those, of course, is how you build models, and they're usually lower levels than what I'll talk about the validation hierarchy in a minute. And the other major tool that is being developed over about the last 10 to 12 years are called validation metrics. You may have heard this term. These are mathematical operators to quantify the difference between simulation and experimental outcomes. And these operators, of course, this idea has been around for a long time, and it's mainly, for example, hypothesis testing is a particular type of validation metric. It has advantages and disadvantages. So what we're primarily interested in here is the determination of how well the model represents the data, but both of them have different sources of uncertainty. Sometimes they're in common, but of course on the experimental side, it has its own sources of uncertainty, which some of them have no image on the modeling side. This is a diagram that was put together a number of years ago, this one came particularly from the AIAA Guide on Verification and Validation in '98. And this is very particularly useful in any type of engineering system where you can refer to it as a complete system, subsystem, benchmark. Sometimes it's called different types of components. and then you have the unit problem. And so this hierarchy is very useful for engineering systems because sometimes you can do many experiments at different levels. You may not be able to do a complete system experiment, validation experiment, for certain sorts of, let's say, safety systems at the very top level. For example, an aircraft system, that validation, a complete aircraft, that's always done. But there are many scenarios, let's say, damage to the aircraft control system, hydraulic system, electrical system. Those are very commonly not done. They get very close to it, but for a complete system, they have the safety issues. The trade-off as you go from the lower levels to the higher levels is you have increasing realism of the system of interest. You may be only interested in the top system or the complete system, but you are building your mathematical models. They are actually built, most of them, or on the lower levels. And then, of course, as you go from the top down, you have increasing information that you can gather because you are dealing typically in a laboratory environment where you have much more control of the system. For example, maybe you have complete measurement of all input data to the model. Model calibration, particularly in the geosciences field, is an extremely important aspect. This is a definition from AIAA and ASME. The process of adjusting physical modeling parameters in the computational model, you could also say in the mathematical model, to improve agreement with experimental data. It's a very specific definition of calibration. And most people don't really think about what they're doing. That's actually what you're doing. It is a particular process to adjust, you could call it free parameters. In fact, some parameters do not exist outside of the complete mathematical model. Many parameters exist separate from your mathematical model, and those you try to determine independent from the mathematical model. And I don't have a lot of time to go into that, when you can determine them independently, when you can determine whether they are fundamentally part of the mathematical model. It's also known as parameter estimation or model tuning or model updating. That's what the Bayesians call it, and that's fine. But I'll usually refer to it as calibration. But it's parameter estimation. And when I say parameter estimation, these parameters can either be scalars or they can be distributions, that is, functions or probability distributions. Calibration is commonly conducted before formal validation activities, almost always. Because you are tuning your model, you are adjusting your model based on data which should be different from the validation data. And there's all different kinds of things, and I just put a few here that should be related to the geosciences field: calibration of erosion parameters and models, calibration of subsurface porosity or permeability, calibration of chemical and biological parameters. There are hundreds, if not several hundreds, of parameters in your models. And these can come from both the system itself or from boundary conditions or the environment on your model. It's usually called excitation in an engineering system. The approaches to model calibration are either frequentist or sometimes are called classical approaches, but just about everybody now uses Bayesian updating. And just a few comments about it, but I'll be glad to answer some questions on any of these topics at the end. Parameters are considered as probability distributions, most parameters, not all, but they're typically considered as they have variability. And in many of these parameters, the variability, instead of in a frequency sense, it is a belief variability, or a belief likelihood. It is a belief of what the true value is. But there's really no single true value because it is indeed a non-deterministic parameter. And the parameters are updated using Bayes' formula when new experimental data become available. And that, of course, is a whole field in all by itself, which I suspect many of you use. And it's very appropriate, but it is primarily a calibration technique or model updating or model building technique. Where do we stand in validation activities? The common approach to validation is actually what, particularly in your field, you may refer to it as validation, but it's actually model calibration. Parameters in the model, either scalars or distributions, are adjusted to improve agreement with experimental data. And that's Bayesian updating. It's exactly what it is. Over about the last 10 to 12 years, what's called Bayesian model validation has grown, particularly with the work of Kennedy and O'Hagan, where they try to identify what we refer to as model form uncertainty, which is separate from the parametric or input data uncertainty. Simulations are usually reliable when the models are used for very similar systems and conditions for which the models are calibrated. That is a reliance which sometimes is very defensible, sometimes it's not defensible. Because as I made the point earlier, and I'll stress later, this whole issue of predictive capability is based on the physics of the model. Weaknesses in the models are actually rarely uncovered, but they are masked because you are using the flexibility in your model to calibrate the parameters in order to obtain agreement with the data. That's actually what you're doing. Like I say, there are many situations where you have no choice because these parameters cannot be measured independently from your model. To improve confidence in our simulations, validation should improve the separation of calibration and validation. This is easier said than done, but you should realize the two different activities as they contrast with one another. Emphasize the assessment of simulation accuracy by using blind predictions of experimental data. When you make a blind prediction, it's a relatively rare situation, but when you are making predictions for an event that has never been seen before, or data which you've never seen before, no one knows the data set except the experimentalist. That is a very useful activity, and that really shows the essence of predictive capability. Improve cooperation and synergism between experimentalists and computational analysts. This is also easily said, but it is difficult to do in practice for many different kinds of reasons at different time scales, typically different funding sources, different cultures, many different things. Predictive capability. It relies entirely on non-deterministic simulation, and I suspect most of you are very familiar with this. But for those of you that are not, I'll briefly show this graphic and talk about what it is. You have various environments of interest, and these can be categories as, in engineering, you call them normal operating environment, or an accident environment, or an abnormal environment. And for some systems, you need to consider what's called a hostile environment. For example, the system is under attack, physical attack, or let's say electronic attack. And then under each environment, each one of these is a particular set of analyses. You have different scenarios. You may have earthquake scenarios, you may have volcanic scenarios, tidal waves, whatever. Those are all individual simulations. And once you get down to the particular scenario for the particular environment, you have two large categories of input data. There are system data and there's surroundings data. The system data is related to geometry, initial conditions, if it's an initial layer problem, and the physical modeling parameters. And that's where most of them live. So, for example, engineering systems, young modulus, porosity, all of those kind of things, those are physical modeling parameters. And then you could also have the other category of input data of surroundings. That is the influence. This is outside of your system. They are boundary conditions, that's the way they show themselves, or they can show themselves by way of system excitation. For example, in an earthquake environment, that's an excitation, let's say, of either a dam or either a nuclear power plant, whatever it is. So these 5 categories capture all of the different kinds of input data, those categories. That presents a vector of input data, which can be very long, tens or hundreds or several hundred long, and you propagate that through the model. And we usually think of the model as the software, but you have to always remind yourself it is actually the physics model, but we mainly think of the computer code, but it actually is a representation of the mathematical model. So that vector X is propagated through, say, the code for now, and it produces a system response vector, and usually the length of that vector is a lot shorter than what X is. Y can be, for example, 5, 10, maybe 20 different parameters, or I should really say different output quantities. Sometimes are called quantities of interest, and that's fine. And if this is a non-deterministic simulation, each one of these is a probability distribution. It doesn't have to be, it can be a scalar. So in this framework, what we're talking about is mapping a set of vectors, which are functions, because the probability distribution is a function, it's not a scalar. It's propagated through a model, and in this talk we will talk about models that are one-to-one mappers. That is, for a given vector input X, it produces one vector output. It can be a probability distribution on the input and output, but you always get the same mapping. In certain types of stochastic modeling of systems, that does not happen. F is actually a stochastic model, but the way we typically do it, by far the vast majority, is to use Monte Carlo sampling on the input propagated through a deterministic model. So we lump the non-determinism into the probability distributions of the input, which map to the probability distributions of the output. So the key sources of uncertainty are in identification of the environments and scenarios that the system could experience that your customer may be interested in, input quantities in the system and in the surroundings. Model form uncertainty is a major contributor, usually the dominant contributor. And then I talked about the numerical errors themselves. Types of uncertainties. You may have heard some of these terms before. Aleatory uncertainties are uncertainty due to inherent randomness of the system or the environment. Sometimes it's called variability or stochastic uncertainty. And these aleatory uncertainties or variabilities, if you like, they are characteristic of the system or of the environment. And I give different examples there. Wind speed, rainfall, natural and variability in man-made or natural materials, those kinds of things. Epistemic uncertainty is a different kind of uncertainty. It is an uncertainty that is due to lack of knowledge, and you commonly have a mixture of the two. But here, I want to define specifically the epistemic uncertainty. It's also referred to as reducible uncertainty, meaning as you add knowledge, which requires time and money, then you can reduce it. And knowledge uncertainty, or Bayesian most usually called subjective uncertainty, and that's fine. So epistemic uncertainty is actually characteristic of our knowledge of the system and the environment, as opposed to a pure aleatory. And as I said, many times you have a mixture of the two. So some examples are underground transport is dominated by epistemic uncertainty. You may choose to represent these as probability distributions, but it really is an epistemic uncertainty. Poor understanding of accident scenarios or event failure trees, and of course, model form uncertainty, for example, in the failure of a large-scale structure. For those of you that are, have not dealt with this whole field of how do you represent epistemic uncertainties, most people represent them with traditional uniform distributions for epistemic uncertainty, but I want to make you aware that they can be represented much more loosely. A purely epistemic uncertainty is characterized by an interval. That is, purely an interval, there's no likelihood of information associated with it. All you can say is that I think I know the minimum value of, suppose it's a parameter, could be an input parameter, and I think I know the maximum value that it could be. And if you represent it as an interval, there's no likelihood associated with it at all. Most probabilistic analyses will put a uniform distribution on that and say that all values are equally likely. You can do that, but you must realize you have added a great deal of knowledge to what was originally said. Originally you said, I have no idea if it's a single value at one end or the other. I know it's so poorly, I can't even write a distribution. I can't even claim a distribution. And then if you have a mixture of epistemic and aleatory, which is the most common case, you actually have something that's called a probability box or a p-box. And a p-box is a special type of imprecise probability structure. And this is a simple one drawn here for an input quantity. Suppose I have both variability and epistemic uncertainty, lack of knowledge, and you could draw them as two cumulative distributions. And what you say, how in the world do you interpret this kind of thing? What it is it says that the cumulative distribution has bounds on it, a lower and upper probability, and all values in between, let's say for this quantity 34, all of those values between, say at a value of 34 from probability of 0.1 up to a probability of about 0.5, all of those are possible, but I know no likelihood. If you put a uniform distribution on that, you will of course have a single uniform distribution, CDF. So this is a much looser structure to better represent epistemic uncertainty. Predictions far from the validation or calibration domain. This is what we commonly do not only in engineering systems but in geosciences. And we usually refer to it as the extrapolation problem. Extrapolation commonly occurs in terms of both input parameters, or another way to have an extrapolation is higher levels in the validation hierarchy. And this is a diagram that we have in our book. Suppose you have a two-dimensional input space, and you have the third quantity as a system response quantity. You have just two parameters, okay? So over that space, let's suppose you have this validation domain, or where you calibrated your model in the light blue color. But we, of course, we almost always make a prediction outside of where we have that data, either from validation or calibration. Large extrapolations commonly involve large changes in physics coupling, or could be completely different types of physics coupling that have never showed themselves inside the domain where you have obtained data. And that is why we stress that its extrapolation is based on the physics in the model. And if that physics is not in your model, then you have no statistical reliability of that, because it's not a statistical problem. So large extrapolation should be based on physics inference, as opposed to, this is not a statistical inference problem, even though those tools are very well developed. The tools of physics inference are not, and I'll talk a little bit about that later. Validation, and here when I say validation, I mean the very specific definition of model accuracy assessment, calibration, and prediction. This is one way to draw it. Suppose you have some computational model which produces a system response quantity, and then you have a physical experiment. Suppose it can be from a laboratory, and then it produces some measured system response quantity, and then those two quantities go into they are input into this validation metric operator, which is a difference operator, and both of these inputs can be non-deterministic, can be distributions, or some operators can deal with intervals. And then you have the validation metric result, which can either be, traditionally it is a probability value, but in some of the more recent validation metrics, it's actually a value. It is a scalar value in terms of the quantity of interest itself. These are much more interpretable than, let's say, you say, well, what do you mean? You could say, if you come up with some sort of probability result, like the model is 90% probability it's correct. Most decision makers or regulatory authorities will say, what in the world does 90% probability mean that it's right? You have accuracy requirements, and those go into the adequacy statement, and that may, if it is inadequate, you may go back and calibrate your models, you may go back and take more experimental data, and then you go to the prediction or the extrapolation problem. This is another way to show it that Tim Tricano and I put together a number of years ago. He's still at Sandia. You have the validation activity or model accuracy assessment, where you have computational results and experimental results, and this could be at any level of the system, or it can be at a unit problem, a very simple laboratory experiment. Producing a validation metric result, you use your model in an extrapolation. You can also, there's a concept called interpolation, but we usually are extrapolating, particularly in a high dimensional input space. Then you have the specifications of the conditions of intended use. These are the environments and scenarios that you are conducting the simulation for. You have system response quantities, or some people call them quantities of interest. And that then goes into the question of adequacy, and in regulatory authorities, that is always the issue. and then you have specific accuracy requirements for the intended use, and then you may go back with a calibration step, or you may then say it is acceptable for use for a particular decision, let's say. This is an example. I won't show you what something looks like if you use imprecise probability theory. This will particularly use a probability box of work from Chris Roy, my co-author. He's at Virginia Tech, and a PhD student working with him, Michael Balch. And this was one that we did, that they did on a prediction of non-deterministic imprecise probability prediction on the performance of a rocket motor due to different kinds of uncertain inputs. Some of these were aleatory, some of these were epistemic, and then you also had numerical uncertainty. And this is how, I won't go into the detail here, but these can be put together in a relatively quantitative way, but how you put all of these together, of course, is still an open question. And some of these also had model form uncertainty. The traditional way that it is done is, I just picked this graphic, which I got from Larry Green he just retired from NASA Langley. This is a graphic he used to make the point of the typical way that you show, like in the previous view graph, you'd say, what is that? The outside bound, that is the outer bounds, are what are called total uncertainty, at least an estimate. But the more common way is using alternate competing models or alternate plausible models. This is a particular state of prediction about 10 years ago with Hurricane Emily, where all of the models were predicted, and I don't know if you could see my cursor or not, but all of the models calibrated to this point in time, and then you had all of the tracks, and this is of course the best way to show instead of some sort of cone, but these are the individual predictions from individual models. And this is a very good way of letting the customer, you could be a homeowner, you could be trying to predict flood controls or whatever you want. This is how uncertain it is. And there's no likelihood associated with any of these. You can go in and assume a uniform likelihood of all of those, but you have lost data with your customer because each one of these would claim they are the right prediction. So this is the common way that is done, where if you have a customer saying we want to have alternate models assessing your predictive capability, is the common one. So a few closing remarks. Code and solution verification, we believe, must be improved to ensure that we're building on a solid foundation for simulation. We have to recognize that you may not be very interested in code verification, solution verification, and all the things that go into that, but this is what we are building on. And if we have a code bug or a numerical algorithm there, or our solution is actually dominated by, let's say, artificial viscosity, and it is polluted by solution verification, and we are claiming the physics because they all get mixed together, we are actually building our bed of sand. Validation is focused on assessing the accuracy of a mathematical model relative to experimental measurements. And in geosciences, that is only a reasonable thing to do, usually in a laboratory environment. In geosciences, mathematical models are dominated by calibration procedures as opposed to in engineering, both validation and calibration are the major activities. And in your calibration, you have almost always, your model is very dependent. You can say it is dominated by the model calibration procedures themselves. Predictive capability is focused on what we have never seen before, and I think that is a good way to describe it. When we make predictions far from our validation or calibration domain, we should concentrate on trying to estimate the total uncertainty, which is usually not a very pretty picture if you try to capture what all the uncertainty is. And I like this quote from Bill Press. He was a senior author on numerical recipes. Simulation and mathematical modeling will power the 21st century the way that steam powered the 19th. I think that gets across very beautifully at the point where we are in the history of science and engineering. Thank you for your attention. I'd be glad to answer any questions.
Thank you very much, Bill, for that introduction to verification and validations. It's certainly a lot to think about as we go forth, and some of us who actually do coding and some of us who use other people's codes to further our research and our models. I swear this is not a paid announcement, but for any of those who want to learn more about the topic, Bill has authored a book along with Christopher Roy, Verification and Validation in Scientific Community, that is available on Amazon and all the other outlets. I don't know if you have any other favorite resources you might want to point people to learn more about this topic or more examples in this topic, especially.
Yeah, in the talk, which I think you're going to make available on your website, and that's fine. I have a couple of pages of references here. Most of them I try to, if I use them inside in the talk. Heim's book, Jakob Heim's, is very good on risk modeling, assessment, and management of all different kinds of systems. And there's a book that Chris and I, that Lorraine was just talking about. And then also this book by Vos, Risk Analysis, a Quantitative Guide. If you've never gotten into uncertainty quantification, particularly in probabilistic simulation, that would be a good one to look at. And there are, of course, in a number of these, they have a lot of other references. So I'd be glad to answer any questions that anyone might have. Any topic, I'd be glad to.
Yeah. So Katie is typing, and if you want your mics open, I'll be happy to do that as well. While Katie is typing, I do want to remind people this is the first in a series of talks. I'll tell you a little bit more about it, so Bill can answer Katie's question.
So can I answer the first question from Katie Cooper?
Yes.
How do we best encourage developers and users to update or to do code verification? That's an excellent question. I wish we had some magic answers to it. We don't. Let me give you a couple of perspectives. We have to realize that all of our simulation results are built on the quality of the coding, the numerical algorithms, and the testing of this software. So we usually try to point out to people, and let's suppose it's either a regulatory authority or an engineering system, let's say a commercial aircraft or whatever system you have. We try to point out to people that if you are using modeling and simulation to make high consequence decisions on, let's say, safety, reliability, performance, whatever you're doing, and you do not conduct your code verification, solution verification activities, then you cannot claim that you are actually solving the equations that you claim you're solving, because you have many, many pieces of machinery to ever get to that result. So if you have a low consequence decision, you want to use modeling and simulation, then you can skip code verification, solution verification. And of course, in many commercials, I would call it, particularly in commercial software, they have some extremely glossy pictures that show unbelievable physics and everything looks great, but actually we are building on the quality of code verification, solution verification, validation, all of the aspects that go into it. So if you have any kind of consequential decision, it is very appropriate that the decision makers who are the customers for this information should ask, what have you done exactly in those topics? And for example, at Sandia, where I was there almost 30 years, the culture has changed tremendously since the beginning of, I talked with Lorraine earlier, about the ASCII program, which is the Accelerated Strategic Computing Initiative. And the culture has completely changed. Now it is no analyst would get up and not be able to answer a question to a customer on knowing exactly what has been done on code verification, solution verification, and validation to their customers. But that's a rare organization that has done that. But a number of organizations are starting to do it, and we hope that people realize that if you want to stay in the world of, sometimes we call it color fluid dynamics, or beautiful marketing picture, you can stay in that world. But if you really want to make decisions, you have to do your homework.
Yeah, I think one of this is bound also in a science culture that is part of the review process and the development process. We do have to encourage people to write papers about their software, and we have to encourage reviewers to ask these questions: how was this model verified and validated?
Absolutely right. And if you're reviewers on journal manuscripts or conference papers, those are very appropriate questions as you as a reviewer to ask of the author. And if they come back with, oh, I have a PhD, I'm really smart, they get an X in my book.
Any other questions people have? I thank you guys for hanging out a little longer because this is a fascinating topic, and we'll actually have a couple of other speakers coming up. We'll also have Habib Najim, who is from Sandia, and he'll talk to us next month about uncertainty quantification in computational models of physical systems. And then we'll have some more science-focused talk with Anna Michalik from Carnegie on climate change, Naomi Petra, who'll be talking about high pi Live, and then also Andreas Fickner in May, who will be looking at seismological applications. So thank you all.
I thought of one other thing, Lorraine, on this question that Katie asked. I should also add in there that if you are at a university and you're a faculty member, then you should include these things in your simulation courses and numerical simulation or whatever you're doing to encourage the students, either undergraduate or graduate students, to be introduced to these concepts, because we have to change that culture. And I think that's another important way that we need to do it.
Right. Let's train the next generation of scientists. Since it's often the graduate students out there who are also training their advisors too.
That's true. Sometimes when you have, in fact, when I was at University of Texas, from your very good students, they bring you into a world and topic that you would never have ventured into before. Any other questions?
So with that, I want to thank everybody for participating in today's webinar. And again, thanks to Bill for spending a little extra time to answer your questions and share his thoughts.
Thank you very much for the invitation, Lorraine, and the best of all to all of you.